For our second presentation here, if we can get everybody to take a seat. Aileen Yingst is a senior scientist at PSI, Planetary Science Institute, that's headquartered in Tucson, Arizona. She is deputy principal investigator for the Mars Hand-Lens Imager instrument on the Mars Science Laboratory rover Curiosity, and she was recently promoted as associate PI of Mars Curiosity rover. Thank you, whatever. She is now the she was participating scientist. She's now the associate PI. She is also an associate on Dawn mission. Other missions include Pathfinder, Polar Lander, and Galileo. Aileen served as director of the Wisconsin Space Grant Consortium for 14 years, and she is now, she received an AB from Dartmouth College in physics, MS, PhD in geological science from Brown University. We will not hold that against her. And so I'd like to welcome Aileen.
Sit down. So, what's the point? Why are we having this workshop in the first place? And I think we've already seen a lot of that from both Kip's talk and the questions that came afterwards. We want to get the highest quality science that we can out of our field work that we do on other planets. And so that's not necessarily an easy thing to do. Quantifying science is hard. Quantifying science is hard because it's a tool. It's a process. We have a tendency to use the word science as if it's a thing almost that exists in and of itself, but it really is a tool. It's a process that we use to look at the world in an organized way. And that can be difficult to quantify. Goals are hard to check off when they are done because they kind of never are. So, for example, for those of you who have worked on missions, think about the goals that you, in whatever role you were in, were trying to reach. If you're an engineer, one of the most common words you will see in those goals or objectives is acquire, and it usually has a number attached to it. For those of you who are scientists in the room, can you tell me what the most common word tends to be in goals and objectives? What is it? What's the verb that we always use? Characterize. When are you done characterizing something? Right? You could characterize me as a female. That's true. Are you done? You can characterize me as a scientist. You can characterize me as half a dozen things in all sorts of detail. When are you done characterizing? So this is one of the reasons that it is difficult for us as scientists to help those of us who are engineers figure out when we're done, right? Because it's difficult to quantify when that actually occurs. So goals are more like facilitating the process. We need to have a process that allows for characterization of the expected or the hypothesized, but also discovery of the unexpected. Our process has to allow for discovery of the unexpected, right? Because geology throws us curves all the time. So it might be better to talk about best practices in a given situation because, again, every situation is different. And we've already touched on that just a little bit, right? Even if we're testing science operations, every situation is different because the goals are different, the objectives are different, the site is different. Even the non-science or engineering factors tend to be different. So the objective here is to determine the best science operations architecture to maximize science, to maximize the science that we get out of a mission. Latency is one of those variables, right? And that feeds into architecture very, very strongly. So let me give you a quick outline and then you can go to sleep. First, we're going to talk about context, definitions, and boundaries. We're going to draw the box. Then we're going to talk about a nominal planning cycle for a long latency or high latency mission. We're going to focus on MSL. We can talk about that in just a second. Then we're going to talk about an off-nominal planning cycle, what that might look like, so that we can have our baseline, and then we can talk about ways that that baseline can change. And then knowing all that information, then we can talk a little bit about, and I mean talk, so if you have a question, I'm talking too fast, or I've missed a definition somewhere, please say something. Then we'll talk about the benefits and the challenges that are introduced in a long latency mission. Key points: time and space are required to do high quality science, and that human or non-science or even non-engineering factors play a crucial role in determining how effective we are on the surface, whether long latency or short. But in this case, we're going to focus on long latency. So our context here is the MSL mission Curiosity. And I've chosen to focus on Curiosity for two reasons. Number one is that many of the science operations, much of the science operations architecture derives from MIR. So if we're studying MSL, in some ways, we're studying MIR as well. The other reason is that MSL is, in my opinion, the most complex science operations architecture that NASA has attempted to use since Apollo. Let me say that again. MSL is, in my opinion, by far the most complex science operations scenario that we have tried to run since the Apollo missions. So there's a lot going on here. And as we add variables, it is only going to get more complex. And so I just want to point out that I had not talked to Kip or Jake before I made this slide. One of the important things to remember here is that very first bullet point. Science operations is a complete system, and that system needs to be examined, to be tested, so that it can be improved as we go. So one other important point here is that MSL has a different science focus. This adds a variable to our equation. So if you look at MIR, MIR is a mission where the main goal is to follow the water. And follow the water means a lot of reconnaissance. The goal for MSL is a little bit different. It's a little more, what is the habitability right here in this landing site or in this traversable area? Regardless, because the science goals are different, the science architecture is going to be different. In the same way, if you were in the field and your goal was to recon a specific site, you're going to take different tools, you're going to have a different traverse, you're going to look at different things, you're going to have different regions or points of interest than if your goal was something different. So I was told to keep this at the 101 level. So what does long latency mean? Latency is basically the time that's required for you to be able to talk to your asset on another planet and to get an answer back, right? A command cycle. Give you an idea of how long we're looking at for Mars, right? So there's an old, just to diverge a little bit, there's an old quote that says, if God had wanted us to be a spacefaring species, he would have given us a moon. And the reason that that is brought up is because the moon is so close. In terms of communications, in terms of latency, we're looking at seconds. For Mars, we're looking at minutes, sometimes tens of minutes. So this graph here, taken right off the web for one of those times where Mars and Earth happen to be close together so that, you get to see Mars in a telescope better than you normally do. Even in these points, the latency between the two planets, if you could speak to Mars instantly, if you could send something direct to Mars and get an answer back, you're still talking about a latency of 8 minutes, 8 to 10 minutes. When Earth is on one side of its orbit and Mars is on the other side of its orbit, then we're talking about a travel time of over 20 minutes there and then another 20 minutes back. So 40 or 50 minutes latency. What that means in terms of science is that you can't joystick it, right? You can't give it a command, you can't give the rover a command and then, I'm going to go out and get some lunch, right? And come back in 40, 50 minutes and send up the other command. So because Mars has this long latency, the way that we have dealt with this is to plan an entire Martian day's worth of activities, send that up to the spacecraft, and while the spacecraft is executing those commands, we are down on Earth planning the next Martian day. So, quick definitions. For those of you who've seen the movie The Martian, you know what a sol is. For those of you who have not, a sol is a Martian day. And this is important because we live on Earth and work on Mars. And so we always have to be very clear about which calendar, which clock we are using. So we might be planning today for Sol 1460. That is mission day number 1460 on Mars. And because Mars day is over 24 hours, those two clocks don't always, in fact, most of the time, do not synchronize. So we have to be clear, are we talking about today on Earth or to Sol, if you will, on Mars? Tactical versus strategic. These are, in terms of MSL, the way we use these words are whether or not we're talking about the Sol that we are planning tactically or the planning that we are doing ahead of time, weeks and months in advance for what's going to feed into that Sol. So strategic is sort of a long-term thing. Tactical is short-term. If you were ever in the military, tactics versus strategy. A pass is our opportunity to talk to the spacecraft and for the spacecraft to talk to us. We have 2 orbital assets, I guess 3 now, that will pass over the spacecraft at certain times of every Martian day. When that happens, the spacecraft can talk to that asset and we can communicate more easily. There's also direct to Earth, but that happens less frequently. A science block for any particular Sol, we are only, on the science side, allowed a certain amount of time that we can use the rover assets to be able to do science, right? Those are termed science blocks. So if I refer to a science block, that's what we're talking about. They can be anywhere from 20 minutes to over 2 hours. They're typically something like half an hour to an hour and a half. And contact science is just the term we use for the times we use the arm or the turret that has instruments on it. So anytime we bring those instruments in contact or in close contact with the surface, if we're limbering up the arm to use it for science, that's called contact science. Here are our resources for those of you who are less familiar with Curiosity. Our science instruments, there are many. I just happen to be pointing at the mast. We've got several science instruments on the mast. We have several inside the rover, several in the arm, which has been, by the way, masked out of this image, but it is there. Anybody who believes that we're not on Mars and you can't see the arm and you're not on Mars, just go to jpl.nasa.gov and all of the pictures are there. We have communications. We have a high gain antenna there, and of course power. And this is different from Spirit and Opportunity in that our power is not solar panels. That's good in the fact that we have a lot more power to work with our RTG. It's bad because it's non-renewable. So this rover does technically have a death date. And of course then we have mobility. In this case, wheels. If you're on the surface, if you're doing terrestrial geology, your mobility are your legs. We have wheels. So let's talk a little bit about this system, the science operations process. A nominal day, and I don't say a typical day because we're on Mars, there is no typical day, but there's a nominal day or a nominal sol, those times when everything works the way we have planned it to work. But this is a funnel, and that funnel starts weeks to months in advance. and funnels into the tactical day, the current SOL plan, which I'll be talking about in just a second. So on the right-hand side of this slide, you'll see the activities that science is carrying out. That's not all of them, but it's some of the more important ones. On the left is the time scale over which those activities occur. The role here, that just means certain groups of people on the science team facilitate those activities, more or less. And then the resources in the funnel, these are the science and engineering resources that we have to play with for science to make the decisions that we need to make to decide on what we're going to do that tactical day. So weeks to months in advance is when really we start feeding into any given tactical SOL plan. And this is through science discussions. It can be formalized through actual science discussions that happen anywhere from 1 to 3 times a week, and various different types of science and instrument discussions. These are facilitated by the LTPs, the long-term planners. And this is a group of individuals who are tasked with holding the general science intent over the long term. So the going hypotheses, the discussions that we've had about what types of observations that we have to do short-term and long-term to be able to test those hypotheses. The LTPs work to hold on to all of those disparate hypotheses and the ways to test them over time. And so they are the facilitators of the science discussions. Not all discussions are formalized. Many of them happen over email discussion. Many of them happen in person. I suspect there will be some face-to-face discussions here about curiosity science. But they all feed into what we end up doing on a specific tactical day. We also have orbital data and knowledge of the spacecraft. Is it healthy? Is it doing all right? Are there any problems with it that weeks or months down the line we're going to have to worry about? And this is the time also where our engineers are starting to put together their plan for the traverse. As science says, look, these are the kinds of things we want to be able to look at. The engineers are saying, well, this is kind of the path that we think is a safe path to take. So there's a lot of handshaking over that going on at this time. In the time period of days to weeks, the long-term planners are still involved, and at this point, the payload uplink leads, or the PULs, also start to take a role, because sometimes observations are very complex, sometimes they're new, sometimes old observations have to be tweaked. And so at this point, weeks in advance, some observations are already starting to be built, and it's the job of the payload uplink leads to do that. So for those of you who are less familiar, a payload uplink lead is someone who works on a specific instrument to design the observations that actually get sent to tell the spacecraft what to do. Uplink, you're sending stuff up in space to the rover. Downlink, it's coming down to us. At this point, we have a little bit more in situ data to play with. We have a better idea of the lay of the land, topography in the meter scale, that sort of thing. We can also look a little bit more in the future and have a sense of the spacecraft position, where it might be weeks, days to weeks from now, what the various sols are going to be timed out as. So we're working on strategic planning at this point. A couple of days in advance, the polls are still working. At this point, the science theme group leads and the SOG chair are coming into play. So science theme group leads, these are individuals who help put together the observations for that SOL, specifically for a discipline such as geology, mineralogy, environment, meaning atmospheres, that type of thing. The SOG chair, the Science Operations Working Group chair, that's the individual who is responsible for carrying the science intent all the way through the process. At this point, we have actionable data. That means that data that we need to be able to make decisions about whether we can go this way in the traverse or that way in the traverse. So getting down to the nitty-gritty points where we're starting to talk about decameter to centimeter scale observations and feeding into engineering so that we know, yes, it's safe to go whatever way we want to go. We also have a notional sense of those really crucial resources: data volume, time, and power. So this is pre-tactical planning. We actually go into any given SOL planning period with a handover plan, a plan where the day before, a couple of days before, they've actually passed on, here's what we think we want to do that day. And all of that work brings us to the current SOL plan, where we have hopefully all of the data down that we need to be able to do what we say we want to do. If we want to drive, we need to be able to see far enough out to be able to do that. If we want to use the arm, we have to have a sense of where everything is because we don't want to drive the arm into a rock or whatever. We also need to know if we have enough power to do everything we want to do, whether our data volume bucket is full or empty or anywhere in between. And we now have a sense of the actual times during the next SOL, during that SOL, where we can do science. And it's at this point that we actually start tactically planning the SOL's activities. So a nominal day of SOL planning looks something like this. Your day starts at 8 a.m. Pacific time. If you live like I do on the East Coast, your day starts at 11 a.m. If, like our French colleagues, you live in France, your day starts at something like 4 p.m. At that point, we actually start putting together the observations that we want to upload to the spacecraft. There are certain days where everything goes exactly as expected. We walk in, and the science theme group lead says, we have the power we expected, the time blocks we expected, and there's not a whole lot to do. That does not happen all that often. Typically when we come in, there are decisions to make. What targets do we want to look at with ChemCam? Or if we're doing contact science, what targets are going to give us the best science on the surface for the various observations that we want to do? We go through that period of essentially horse trading. And at this point, we're talking to the engineers through the SOG chair and through the polls and through other individuals to know how things have changed. Well, maybe we want just a little bit more time on this science block because we want to add one more observation. Maybe we want to move the science block completely because we have this beautiful mosaic that we want the mass cams to be able to take, and the better lighting is 2 hours later or something like that. Well, that runs into when the rover's supposed to be repowering, it's supposed to be having a nap, or there's supposed to be a pass by Mars Reconnaissance Orbiter when we need to talk to another spacecraft or something like that. So there's a lot of horse trading at this point that goes on. But you'll see a big line here where it says SOG meeting. So the left-hand side of this is mostly science-driven activities with the engineers telling us, yes, you can, no, you can't, let's see what we can do for you. On the other side, this is where science kind of goes into the strategic mode for the next several SOLs, and the engineers are really putting together the plan that's going to go up to the rover. The SOG meeting, the Science Operations Working Group meeting, is where those two groups shake hands. And as Jim alluded to, one of the real benefits that has started with the Mars Exploration Rover Spirit and Opportunity, and in my opinion has continued with MSL, is this ability for scientists and engineers to, at least on some level, speak each other's language, to understand what is important to the engineers, to have the scientists understand what's important to the engineers, to have the engineers understand what the scientists are trying to do at any given place. So one of the great ways that we maximize our science from MSL and MER as well, as the more obvious example, is this ability for scientists and engineers to be able to walk in each other's shoes, to understand the language that each one is speaking. And we'll talk a little bit about how that language differs. But we've already seen that already. It's the difference between acquire and characterize. And understanding that both of those points of view are valid and crucial for a successful mission is one of the things that, in my opinion, has made MER and MSL successful. So the SOG meeting is that last opportunity for puts and takes in the plan, changes in the plan, making sure that everything is the way we want it to be, to make sure that the science intent is carried as well as can be, as it moves up to the engineers finalizing the plan. After the SOG meeting, the SOG chair actually stays with the tactical process. So the SOG chair stays as the carrier of science intent. So if there are any questions that come up later on during this period where the engineers are finalizing the plan, the science intent can be carried through. There are major problems that have been seen, there's less power than we thought we were going to have, or whatever. Having the SOG chair there makes sure that the science intent can be carried out. Sometimes it's even something as simple as, we thought we were going to be able to get this target, can we move 5 millimeters over and still retain the science intent? The SOG chair is there to be able to answer that question. The rest of the science team has moved on to strategic planning or pre-tactical planning of the next sol or sols that we're going to work on, and then science discussion, where the top of the funnel is. And we could be talking about anything from what we're going to be doing in the next couple of days to the next couple months. So we have an idea what happens with a nominal sol. What happens when things don't go as we expected? What does an off-nominal day look like in planning? Well, it turns out that this is one of the challenges with long latency, because recovery takes typically at least the sol that you missed, right? And sometimes longer, and sometimes some science never gets recovered. So I'll address that just a little bit later when I talk about benefits and challenges. But for now, remember that because we have long latency, because we're not joysticking the mission, if there is a fault that occurs, we don't know about it until the next time we speak to the spacecraft. We don't know about it until the next sol, or until the next day, I guess is the appropriate term to use. So, when this occurs, and for the most part, it's not a serious fault that occurs. That does occur. They're rare. What often happens is that the tolerances for roll, pitch, and yaw or something have been set just a little bit lower than what we really needed for that particular type of terrain or something like that. But regardless, the rover hits its tolerance level and says, "Boop, I'm done. You let me know what you want me to do, because I'm done." And that fault can occur for many different reasons. That type of fault can occur for different types of instruments. And it can happen at the beginning of a sol, it can happen in the end, it can happen anywhere in between. So what are the usual outcomes at that point for science? Well, one is you have a stand down. Those are the scary ones. Those are the ones where the engineers tell the scientists, we're not sure, we don't want to hurt anything else, we don't even know if we've hurt something, we're just standing down, science can go home, because we're not doing planning today. This actually, as long as everything works out with the rover, can have benefits because it gives us a whole day to be able to talk about science, to talk about some of the data that we've received already, and what that might have in terms of implications down the road and so on. Another possibility is Groundhog's Day, which is just another way of saying, let's repeat it. Let's do the sol we did. We're pretty sure we have this fault figured out. We're just going to repeat the sol. We're done. Typically, we don't completely do a Groundhog's Day because those resources that we were talking about, power, data volume, time, they change from sol to sol. So the more typical outcome is a plan B. And it can be as minor as we're going to repeat what we did last sol, except this particular science block has to be a little bit shorter because we're lower on power and we need a little bit more time for the drive or something like that. Sometimes we have a completely different sol scenario. Science blocks can't be where they were before, or we were originally supposed to have a pass that gave us 250 megabytes. Now we have one that gives us 50. And so that totally changes how we're going to set that plan together, how we're going to put that plan together. So again, the typical scenario here is that we're scrambling because we have to have a plan B. Oftentimes, we will have a list of leans, things that we'd like to do but haven't had time to do yet. Sometimes we can just pull from that list. And sometimes, when we know there might be a problem for the next sol, we've actually planned a plan B. If we get this data, we're going to go this direction. If we get that data, we're going to go that direction, right? So you begin to see, after all of these slides that I've been showing you, how important that lead-up planning is to make that tactical plan run smoothly when we finally get to that point. And one of the reasons that's so crucial is because when you get to tactical planning, you don't want to have 5 minutes to make a really, really crucial decision. You want to have had a lot of that mental effort expended prior to this. So, but you can see in this case that the effect on science is going to be mixed. Usually it means we lose some kind of science, although sometimes actually things can get better. Instead of having this really anemic pass, now we have this huge pass. So would you like an extra 30 minutes on your science block, that kind of thing. And that's when the lean list comes into play. Some observations are more hypothesis-driven, some are more systematic and can possibly be taken later. Some are time-sensitive while others are not. So all of these things come into play. And again, you can see how much horse trading goes on through all of this scientific process. The trading between engineering constraints and science desires, the trade between what we want to do and what we have the resources to do. So what? Now that we have an idea of what long latency looks like in action, what does it mean for science output? And as I go on at this point, I want you to understand that this is my understanding of the benefits and challenges that are involved here. It comes from experience with MUR and MSL. It also comes from baseline analog testing and that desert rats, the ghost field tests that we've been doing. So I expect my opinions to evolve over the course of this workshop. I expect some of my opinions will completely change, so I'm looking forward to that. So, what are some of the benefits of long latency? One of them is that you have a large team. Now, can you have a large team with low latency? Sure. But the idea of having 200 people over my shoulder while I'm joysticking is not necessarily something that appeals to me. We were talking earlier, and Bob said if you have 200 scientists in the room, you have 500 opinions. That's probably pretty accurate. And so the more team members you have, kind of the more time you need for all of those opinions to kind of percolate and bubble and cogitate and get to the point where we kind of distill down to the truth. One of the other benefits is that you have natural stopping points in the process. Very clear, very formalized natural stopping points, which means that systematic data collection tends to be easier. And this point comes more from my experience with analog tests. And we found in many of those analog tests that the systematic data that allows us over the long term to really feed into hypotheses, we tend to forget to do when we have short latency, when we have low latency, when we're able to joystick. We tend to forget, oh yeah, we're supposed to be taking, we're supposed to be dropping a sensor every 15 meters or something. We forgot to do that. Well, we've been involved in this. So long latency actually gives us those natural stopping points that allows us to take systematic data taken methodically or according to plan on a regular basis. And this is important for science because it means we get to go back and check that data out. Well, have we seen this before? Well, we've been taking these class surveys every time we've stopped a drive, and we can tell you that these particular types of pebbles we saw back on Sol 455, and they look very similar to the ones we're looking at now, or whatever. The most important benefit that we get, I think, from long latency is that it has built-in time and space for science to happen. And I have that in quotes. I'm a little uncomfortable using that term, happen, but it's the best way I can think of to describe it. It's crucial to have time for hypotheses to develop, for ideas to percolate, and for people to discuss and butt heads and debate and do all of those things that really draw out the best conclusions, right? It's very much like refining a metal. You need to be able to beat an idea and really draw out the best of it. And that takes time, right? And to a certain extent, that's human-driven. But we're humans, and we have to look at things as they actually are. So, what are some of the challenges of long latency? Well, we've addressed one of them already. Sometimes it means significant loss of science data, right? Because again, if the rover hits a specific type of fault, it's not going anywhere until we tell it what to do. And when that happens, you can't necessarily negotiate it in near time or near real time. Another issue, and I think this is really important, is that the tactical process especially, the tactical timeline can be very fast. And as Jim pointed out, even in long latency, we're learning a lot of lessons that can be and should be applied to a low latency mission, and this is one of them. The tactical timeline can essentially be in a small area, low latency. You may have to make decisions very, very rapidly. If your decisional data, that is the data that you need to be able to make the decisions about that particular sol, comes down late in the process, you may only have 10, 15 minutes to decide on what the best target is for your contact science, or whether we're going to go or stay, whether we're going to drive on or whether we're going to do contact science or whatever. And that tactical timeline means that scientists are working counter to their training. A good scientist is trained never to rush to judgment. We are trained never to make snap decisions. We're trained to let all of those conflicting hypotheses work themselves out, test them methodically. So the tactical timeline means that scientists are working counter to their own training. And there are non-science factors, and we will continue to have these as long as we have people, right, doing these missions. One is the initial makeup of the science operations team and the engineering team. Another is the day-to-day makeup of the science operations team and the engineering team. So for many scientists, we have other responsibilities, other grants that pay us, other jobs that we are responsible for. If you are Professor Hodges, my guess is that you've got classes that you have to teach, and so you're not going to be working 100% time necessarily on MSL. Maybe you've got 25% time. If you have 25% time, that's a week out of every month, which means 3 weeks out of that month, you're doing something else. You may not necessarily be plugged into the mission. And so the expertise and the knowledge that you bring when you call in for that week is going to be different than if you could have or wanted to devote 100% of your time to that mission. It's true for the engineers as well. There are certain roles that you have to train up for. And if that role is not filled that day, you need a person to be able to command the arm. Well, we don't have that person on shift today, so you're not doing contact science. Other logistical factors, well, scheduling. Certainly, many of us were there for 90 sols, the first 90 sols of the mission, but we have loved ones that we want to go back home to, and so we're now down to 5 days a week, and we're on an 8 a.m. Pacific start time. So what that means is that you have scheduling issues that change your team makeup. You also have scheduling changes due to anomalies. Do you drop what you were going to do, or do you move on? So again, a brief summary here. We have a benefit, and I think the main benefit of long latency for science is that it gives us time and space to work science problems, to play out hypotheses and figure out the best ways of addressing them based on the data that we have. Some of that benefit is undercut by the non-science factors that I introduced. And of course, the fact that problems can take longer to diagnose and correct with long latency than they might with low latency. So I also like to have a discussion rather than me yakking. So I'm going to close it there and ask for questions.